welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We both are from Civil Engineering Department, IIT Kharagpur. We have divided this course into two parts. The first part is environmental chemistry, that will be covered by me, and the second part is environmental microbiology, that will be taught by Professor Sudha Goel. Now, this is my 28th lecture and this is module 6. In this module, I am covering the radioactivity chapter or nuclear chemistry. As you can see here, in my previous two lectures, I have discussed about the fundamentals of radioactivity, and in this lecture, I will cover the following topics. The lecture content is shown here: a radioactive disintegration series, nuclear transmutation, artificial radioactivity, and age of the ore or rocks I will discuss. Radioactive disintegration series, as you see here, that there are many radioactive elements that we know, and mainly among the elements having the atomic numbers from Z equals to 81 to Z equals to 92, in this range there exist many radioisotopes. By now you know what does it mean by Z, and what do you mean by radioisotopes. So, in this range there are many radioisotopes. They can be grouped mostly into three series. Okay. And how they are classified, they are placed in these three series. One series is defined by thorium, that is 4N series, another is by 4N plus 2, that is the uranium series, and the third one is 4N plus 3, that is the actinium series. Here it is shown 4N thorium, 4N plus 2 uranium, and 4N plus 3 actinium. Now, what is the speciality? Here N is an integer, obviously. Each series is characterized by a single long lived parent isotope and a common end product, which is a stable isotope of lead. So, end product is for all the series, the end product is lead, but you can see here that they are isotope of lead. In this case 208, that is the mass number, and here it is 206 and here it is 208. And what is 4N plus 2 and 4N plus 3? If you divide this atomic mass number by 4, then you will see that there is it is coming as 4N, in this case 4N plus 2 and 4N plus 3. Okay. So, thorium, uranium 238 and uranium 235. This is also called actinium, okay, actinium series. Now, T half. It is also characterized by the T half. I told you that this is a very characteristic thing from the for the radioactive elements. Okay. So, this is the 1.39 into 10 to the 10 years, this is the half life for this one thorium and for this thorium, and then this one 4.5 in 10 to the 9 years, this is the half life for this uranium 238, and 7.07 in 10 to the power 8 years, this is the half life for uranium 235. So, these are the three series. The separation, isolation and concentration of radioisotopes has been developed as a new field of interest. Okay. So, when there are many radioisotopes formed, it is very important to separate them, to isolate them, to study their properties, to use it for other purposes. Okay. So, this is very important field. Now, this is a very important experiment done by Rutherford in 1919, nuclear transmutation. Nuclear transmutation means that is some type of reaction by which one nucleus is transformed into another. Previous to this, we did not know that one atom can be transformed into another, okay, but this is the first time Rutherford did it. You see here, it is a famous alpha particle bombardment experiment done by Rutherford. Okay. What it did, nitrogen upon bombardment with high speed alpha particle, okay, this is the source. Okay. So, from this this is a radio element. So, from this radio element alpha particles are coming out, that alpha particle high speed alpha particle he has used to bombard the nitrogen. Okay. And when he did so, then what happened, what is the product? An isotope of oxygen and proton. Okay. So, here it is shown nitrogen, you know the atomic mass number is 14 and atomic number is 7, and this is the alpha particle means 4 and 2, and then when this bombarded here nitrogen, then what we get, oxygen, this isotope, oxygen is 16 here, but it is 17. So, it is an isotope of oxygen and 8, atomic number is 8, and proton is produced. Okay. Although there was sufficient absorber, how to understand this? There was sufficient absorber to absorb the particles, to absorb alpha particles. Okay. So, you have seen the properties of alpha particles, that it can be easily stopped. Okay. So, even if there are absorbers, sufficient absorbers to absorb the alpha particles, still he has observed the scintillations, flashes, bright flashes, okay, observed on zinc sulphide screen. So, what is the reason for that scintillation or flash? These are due to the protons that is produced. Okay. So, but you know that when he did the experiment, when he wanted to publish it, people did not believe. They thought that it is the impurity, oxygen was already there. So, it is not produced, but it was already there. So, it is observed, but finally it is seen, it is observed by him, it is proved by him that it is the product of nitrogen. Okay. So, it is called transmutation, nuclear transmutation, one nucleus to another nucleus, nuclear transmutation. Okay. Important experiment, very important experiment to understand the things. Okay. Another important experiment, that is by Irene Curie and F. Joliot. Okay. Who are they? Irene Curie, who is she? She is the daughter of Madame Curie. Okay. So, Irene Curie and her husband F. Joliot, okay, they were also doing some experiment to find out the neutron, okay, on neutron. Okay. Now, they also got the Nobel Prize, not for Newton, but they got the Nobel Prize in 1935. Okay. For what? For artificial radioactivity. Till now we have only seen that radioactivity is coming out from heavy nucleus, and that is spontaneously it is coming out. So, it is natural radioactivity, but this is the artificial radioactivity. So, and how they got it? Bombardment of aluminum, you see aluminum with alpha particle, they were doing lot of experiments. That time lot of experiments, radioactivity was discovered, alpha particles with bombardment with alpha particles, all those types of experiments are going on to find out some particles, to see the behavior. So, they were also doing some experiments, and then what they have seen, what they did actually, they have bombarded the aluminum with alpha particle. Okay. The alpha particle they got from the from polonium, it is also radioactive element. So, they got that from polonium. But what is the observation? Produces neutrons and positrons along with the emission of a radioisotope of phosphorus. This is the artificially produced radioisotope of phosphorus. It is artificial radioactivity. So, artificially produced radioactive element is nothing but this one, radioisotope of phosphorus. Okay. So, this is two step, there are two steps. and this has very having half life only 3 minute, okay. Transient existence, okay, only 3 minute half life, okay. Now, what is happening here? You see that if you look into this phosphorus 30 and 15, actually for phosphorus natural isotope is 31, 15, but here it is radioisotope, it is 30, okay. And next step, you see this one is very transient existence, only 3 minute half life, this has converted to silicon, 30 and 14, okay, and positron, okay. Positron, electron you write E minus, positron means positive electron, so it is written as E plus. So, here both neutron and positron are produced, but this is the new thing that they have observed. This is nothing but isotope of phosphorus, but this is radioisotope, means it is immediately it is disintegrated, okay. Following this discovery, many radio elements were produced by irradiating stable isotopes with appropriate nuclear projectiles. What is projectiles? They are the particles by which you can bombard some nucleus, okay. Say they can be proton, they can be deuteron, they can be alpha particle, they can be electron, they can be neutron. So, they are with high speed, they are bombarding the nucleus, they are called projectiles, okay. So, this is the very important experiment, and they got the Nobel Prize for this artificial radioactivity discovery. So, in one family you see that Madame Curie got 2 Nobel Prize, and this is the 3rd Nobel Prize that came in the same family, okay. This is Madame Curie's daughter. Now, artificial radioactivity, there is some mechanism that has been given by Bohr in 1936. How it is coming? Nucleus to be disintegrated, nuclear projectile. So, they will form some compound nucleus, but they will have very short, they are very short lived. So, compound nucleus will be forming the product nucleus and with the emission of particles. So, this is the theory given by Bohr, okay. The compound nucleus is very short lived, okay. 10 to the power minus 14 to 10 to the minus 12 second, this much, very short lived, okay. Now, this is a very important application of radioactivity, okay. You can determine the age of a rock or ore, some ore when it is produced, okay. So, age means when it is produced, okay, that you can determine, very nice concept, okay. There are 2 methods I will discuss. The first method is from the, say for example, it is uranium ore, okay. So, first is the uranium ore, uranium lead ratio. From the uranium lead ratio you can determine the age of the rock, uranium rock, okay. Let us consider a rock containing uranium, okay. This is formed long years ago, long time back it is produced. The uranium started to decay following the, this is the step, uranium 238 is decayed to lead 206, okay. Now, the half life of the intermediate members are very small compared to uranium 238, because we know that T half of uranium is this much, 4.5 into 10 to the 9 years, that we know, okay. Now, the uranium lead ratio, if we can determine chemically, by chemical analysis it is very easy to determine uranium lead ratio. At present, how much is the uranium, how much is the lead present at present in the ore, that we can determine easily, okay. So, we can determine it. From that ratio it is possible to find out the time elapsed since the formation of the parent element, how much time has elapsed when it is first formed and at present how much time has passed, that is the age, right, that is the age of the ore. So, that we can determine, okay. In this way the age of the earth was also, say for example, the ore is long time back it is produced, it is when the earth is also in the beginning. Okay. So, that time if it is there, from that time if it is there, then age of the rock and age of the earth is same. Okay. So, that way age of the earth was also estimated, and it is pretty close, means good result was obtained to know the age of the earth. Now, let us do one problem with this particular with this topic by knowing the uranium lead ratio. So, an uranium ore contains 11.9 gram of uranium 238 and 10.3 gram of lead 206. Calculate the age of the ore. So, what they are supplying? They are supplying the at present how much is the uranium and how much is the lead in the ore, that is present, at present how much is there. Okay. Then we can, if we can determine at the beginning how much was there, then we can easily find out the time elapsed. Okay. Now, here you can see from 1 uranium we are getting 1 lead. Okay. That is very important, 1 uranium gives 1 lead. Okay. Now, this is the formula that that is required to know the T, the time that is passed. Okay. Elapsed. Okay. So, this is required. So, to know this we have to know the lambda, we have to know N 0 and N is already given at present how much is there, N 0 we have to know. Okay. So, this way lambda we have to know. So, lambda is 0.693 by T half is given. So, we can easily find out lambda. Now, 11.9 gram of uranium 238 is now it is present. Okay. It is present now, and uranium ore contains attogram of uranium. So, this is at present uranium concentration, that is nothing but 0.05 mole. How you are getting? By dividing it by this. Okay. Now, lead, at present lead is this much. So, how many moles? This one. Okay. So, mole of uranium present in the ore in the start, how much? That is 0 time, that is nothing but at present how much is there and how much lead is produced, that is coming from the, because the ratio is 1:1, the stoichiometry is 1:1. So, 0.05 plus 0.05, that is the beginning N 0, this is the N 0 value. So, you can put N 0 0.1 and N 0.05, that is nothing but 2. So, after putting all the values you get 4.5 into 9 years, that is the age of the ore. Okay. It is means concept is very good, application is also very good, the calculation is very simple, very simple. There is another method, that is also from uranium, but that is from uranium helium ratio. Okay. Why helium? Because it is producing, that I told you that alpha particle, it is giving out alpha particle. What is alpha particle? Alpha particle is nothing but helium nucleus, isn't it? So, helium nucleus, then is it positively charged nucleus, then how can you know that it is helium? You can easily find out from atomic spectra. Okay. If you see the atomic spectra, you will get the characteristic spectra of helium atom. So, that way you can understand, okay, this is the helium. Okay. That way actually it is detected as helium in alpha particle. Now, these are the key points that you have to remember for this. When an atom of uranium 238 disintegrates, it produces these 8 alpha particles in the chain. Okay. So, after 8 alpha particles, after leaving 8 alpha particles, it goes to the end product, okay, lead. Now, the helium atoms are trapped within the ore and retained. It is in the ore, inside the ore. So, helium it is producing, it is trapped in the ore, it is trapped inside the ore. Okay. Now, it helps to find out the time elapsed since the ore is formed. When the ore is formed and by now, you can the time you can find out you have to know how much concentration of helium is produced, how much helium is produced. Okay. From there you can know that how much time now is passed. Find out and another thing, this method is not very accurate because some loss of helium always occurs. Some heliums by diffusion escapes out. Okay. So, some loss is there, not all, but some loss is there. So, this is not that accurate, okay. But still you can get the idea. Now, what is the problem means numericals you see here, find out the age of the ore which contains atto cc of helium at STP and atto gram of uranium 238, T half is atto. Now, from this I have given only clue, okay. You can do it by yourself, you can try. Let us assume that x number of helium atoms are present, 22.400, 22.400 cc at STP is equivalent to Avogadro number of helium atoms, that we know. So, this much cc at STP is how many atoms? When an atom of uranium 238 disintegrates, it produces 8 alpha particles. For each nuclear transformation to lead, 8 alpha particles are produced. That you have to remember and you have to use this. Uranium atom disintegrated, how much you have to calculate? Uranium atoms left, okay. This is given, contains atto helium and atto left. So, this is left. Uranium atom originally present N0, how much is disintegrated plus how much is left, that will give you N0 just like the previous one, but in this case helium, that is gas. So, in terms of atom you have to calculate. Okay. Then finally, this is the equation that you have to use, you have to find out the T, lambda is known because T half is known, N0 you have to find out, N is given, N0 you have to find out. N0 means the now it is now how much is present plus how much is disintegrated. So, how much is disintegrated, that you can find out from the helium, okay. How much helium you are obtaining from there, how many atoms of helium you are obtaining, and for each uranium atom 8 helium atoms are produced. So, that also you have to consider. So, you can try this, this is very means interesting problem, okay. You can try this. Now, the references, the same references that I have already shown you, you can read from this book. Actually, the last two problems, you know, last two problems, it is in some books you will see that it is the age of the earth. It is written how to determine the age of the earth. This is also called geological clocks. Geological clocks. In clock, what we see is time, right? It is also time you are seeing, how much time is gone. Okay. So, geological clocks it is called, and age of the earth, the topic title is age of the earth, but basically you are determining the age of the earth via the age of the rock, means rock if you can find out, if you think it is produced at that time only when earth is the beginning of the earth, then you can tell that it is the same. Okay. So, very important thing. So, in this lecture we have means seen how the radioactive disintegration series, what are the radioactive disintegration series, they are classified, and then we have seen the Rutherford's experiment on nuclear transmutation, how one atom can be transformed into another, okay, and then artificial radioactivity that is developed by Irene Curie and F. Joliot, and then how the age of rock or ore we can determine by using two methods, and then which can be related to the age of the earth. So, this on the basis of the radioactive decay, theory of radioactive decay, and then half life and all those things that we have learned, that on the basis of that these numericals we can do. Okay. So, very important for radioactive chapters. Thank you.